going to do the changing area. Let's say we've got this wire going like that, and we've got a magnetic field going into the board in that region. Now, outside of this, I don't care what's happening. Just looking at inside of this. I've got another wire right here. And this wire can slide along these two wires. But they're connected electrically. They're not insulated from each other or anything. They're touching each other electrically. And this one's going to slide. Well, what if I move this wire to the right? Well, as it moves to the right, then this area that's in here gets larger. So the magnetic field staying constant. Angle between the area and the field, which in this case is 0 or 180, is constant. But the area is getting bigger. So as the area gets bigger, the flux changes. As the flux changes, you induce the voltage. So which way is the current going to run due to this area getting bigger here? Well, if I think of it in terms of Lenz's law, as this area gets bigger, I get more and more of these flux lines going into the board, inside the area. Which means the current wants to oppose that voltage induced and the current that's going to be produced by that voltage wants to oppose it, which means you want to have the current to produce some magnetic field lines coming out of the board toward you instead of going away from you to try to cut down some of these extra field lines going into the board. Try to limit it. Well, if these field lines are going out of the board due to whatever current, the current has to either be going clockwise or, clockwise this way or counterclockwise that way, from here around like that or around the area that way. As this wire is moving, now if the wire is stationary, you don't get any induced voltage. You have this moving wire going across here. Well, if the current's coming out, the magnetic field due to the current is coming out, which way is the current? So pick one of the four sides. So if I pick this bottom side, well, actually, I'm going to pick this vertical one, the wire itself. In order to have, in this region, to have the current coming out of the board, go back to my second right-hand rule. Thumb in the direction of the current, fingers go around the thumb direction of the magnetic field. So if, I'll choose the wrong one first, if my current was coming down, then over here on to the left of it, my fingers would be going into the board. But that's more X's. I don't want X's. So if I have my current going up, then on that side, my fingers are coming out of the board, and it doesn't matter what's happening on the other side here. It's only what's happening inside the area. So I would have them coming out, so I want current going this way over the top. That means it has to go like that. And again, below it, my fingers would be coming out of the board. On this end, fingers thumb going down into the right of that. Do that. Now on this side, fingers are coming out of the board and down here on the bottom. If it's going left to right, above it, fingers are coming out of the board. So current would be going around counterclockwise for this particular situation. Tell which direction the current is, but you're applying what's called Lenz's law to do that. By the way, the other way you could get this, if you think of in this wire, you've got electrons, that are free to move. So as the electrons have some velocity here to the right, which way is the force on the electrons? Go back to the first right-hand rule. Field's going into the board, electrons are going to the right. Force on the electron would be downward, right? That's a negative charge, which says this end of the wire would become more negatively charged, this end would be more positively charged. You separated the charges, positive and negative charges, which means you've got a potential difference across there. But if you've got positives and negatives, remember, like a battery, the current goes from the positive around to the negative. So current would be coming this way and going around here. And of course, this would be like, this was a battery, it'd be like the internal part of the battery moving across here. So it would be going like that also. If you were pushing the wire the other way, force on the electrons would be up. So the top would be negative, bottom would be positive, and the current would be going the opposite way around the loop. You got a changing area. So you got all this Lindsay's law stuff, which make nice quiz questions, but test questions probably not. Test questions is think of this. If you were given either flux as a function of time, B is a function of time, A is a function of time, or theta is a function of time, then you could do this voltage as a function of time by doing the pt. And again, with like the electric generators, what's changing with time there is the angle between B and the A, which gets you into the alternating currents that we'll talk about hopefully Wednesday. So that's Faraday's law of induction, and that's probably a good place to stop. We still have a left to do. Whatever that chapter is. Okay, 29 on the the big equation out of chapter 29. There's one other we're going to talk about. Just a particular example we have. So, put the steering and measure and measure.